All right, we are coming back to section 2.4. We've already gone through long division, so skip down past those examples. And we are right here, dividing polynomials using synthetic division. Now, the last thing that I want to talk about before we get into this is the division algorithm. The division algorithm simply says that whatever my original function is, if I divide it by some function d of x, then I can write my equivalent function as what I'm dividing by times the answer, the quotient, plus the remainder. Now let's think of this in terms of regular numbers first. If I wanted to do, say, 5 into 17, okay, that would be 3 with a remainder of 2. I could say, using this division algorithm, that I now know that 17 is equal to 5 times 3 plus 2, which makes sense. 15 is what multiplies out evenly, and then 2 is what's left over. Okay, now this works the same as if I wanted to do something like 5 into 25. It goes in 5 times with a remainder of 0. So we can say 25 is equal to 5 times 5 plus 0 because there is no remainder and we don't need to write that. It works exactly the same way with polynomials, but that's kind of an easier way to interpret that. Okay, what we're looking at today is a new technique for dividing polynomials called synthetic division. You may have learned this last year, I don't remember. It's a much quicker way to divide. You can see the long division algorithm compared to the synthetic division algorithm for the exact same problem. And the synthetic division is much shorter. However, it is critical to know that synthetic division can only be used for dividing by a factor in the form of x minus c. What that means, it must be a linear factor, x to the first only, and it must have a coefficient, a leading coefficient of 1. So x minus 2, great. 3x minus 2, can't do it. If you have that, then you're going to have to use long division. So that's always the question I get after we do this is, well, then why do we have to know long division? Because most of the time, synthetic division doesn't work. It only helps you divide out linear factors. So that's really an important thing to note, and I would definitely put that on a flashcard. So here is a summary of the steps for this. Now, this is really going to be helpful to you as a reference after I've shown you how to do it. So we're not going to read through all of these, but the first 2 steps are really important for us to get started. First, we need to make sure that our polynomial is in standard form and that we put in zeros for missing coefficients as needed, just like with long division. To set it up, we're going to use the opposite of c as your corner number. So remember, the factor is always going to be of the form x minus c, so we need the opposite. So if I see x plus 5, my corner number is going to be negative 5. It's kind of like the h in the vertex and things like that. You always have to flip the sign. Okay, so here is how we set this up. You can go back and read through those steps after we've done a couple. So first, I need to look at my factor and verify that it does meet the requirements. The corner number here is going to be negative 2 because we have to switch the sign. I see plus 2, so I'm going to use negative 2. The other thing I notice is when I look at my polynomial, it is in standard form, but I am missing an x squared. So we're going to have to make sure that we put in a 0 there. Now here's how we set this up. I use a big long L. The book uses just a little corner L, but this is how I always learn to do it. The corner number goes on the top up here. That's C. Okay. And then we line up just the coefficients. No variables go in here. So 5x to the third, 0x squared, 6x, and then 8 is our constant. And here's what we do. We always add the columns and we multiply by the corner number. So the first thing that we do is we bring down the first number. So I have 5. The outside numbers always get multiplied by the corner number. So 5 times -2 is -10, and that fills in the next column. Then we add the columns. So 0 plus -10 is -10. Now I take my new outside number and I multiply it by the corner again. So -2 times -10 is positive 20, and then I add my column and I get 26. And then I multiply by -2 and I get -52. And when I add, I get -44. This last number is always the remainder. These three build our answer, okay? So since the original function started with a cubed, my answer is going to start with a squared. It always starts 1 degree less. So the answer here is going to be 5x squared minus 10x. We just work our way down in powers, plus 26. And then the remainder is going to be minus 44 over x plus 2, just like when we did long division. So that's the answer that we get. Remember, bring the first one down, and then you multiply by the corner number to fill in the column, and you add up the column. Then do it again, fill in the next column, add up the column. So pause the video, please, and try number 6. I'll come back with the work in 3 seconds. All right, here's how you should have it set up. Make sure you got that 0 in there. Make sure you have the right sign on your corner number. So we multiply 1 times 1, which is 1. We add 0 plus 1, which is also 1. Again, 1 times 1, which is 1. We add, we get -6. -6 times 1 is -6. Add the column to get -12. And so our answer should be x squared plus x minus 6 minus 12 over x minus 1. And that's what we get. So this is a much, much quicker way than long division if you're allowed to do it. And you have to make sure that you know when it is appropriate to do it and when it is not. All right, so using synthetic division, because it's especially quick, we can do some other things. So the remainder theorem says this: if a polynomial f of x is divided by x minus c, then the remainder is always going to be f of c. This is going to be important in future theorems, but what this essentially allows us to do is what is sometimes called synthetic substitution. If I want to plug in a number c, then the answer, if I plug it in, is going to be the same as if I divided by the factor that goes with it. So for example, on number 7, if I have this function f of x and it says use the remainder theorem to evaluate f of -4. Now we could just plug in -4 for all of the x's, but if we were to do that on this question, it would not be a full credit kind of answer, because this question is asking us to apply the remainder theorem. The remainder theorem requires us to use synthetic division. They've given us here, this is f of c, so c is -4 in this case. That's going to be our corner number, -4. And we're going to line this up, 1, -4, 5, and 3. That's just based off of the polynomial. So we work our way through. Bring down the 1, multiply, add, multiply, add, multiply. I think that's going to be -148, and add, and we get -145. Now, all we want is the remainder. If I want f of -4, the answer is the remainder. So to answer the question, f of -4 is equal to -145. That's it. F of c is equal to the remainder. Sometimes that's a lot easier if you don't have a calculator for plugging in numbers. Okay. Now the factor theorem is an extension of the remainder theorem. It says if f of x is a polynomial, then two things are going to be true. If f of c is equal to 0, then that means that x minus c must be a factor of the function. And the converse of that is also true. If x minus c is a factor, then that means f of c is equal to 0. Now don't forget what the factor theorem just told us. the remainder theorem, whenever we're talking about f of c, that is the remainder, which makes sense. If I tell you that 5 is a factor of 20, that means that 5 goes into 20 evenly with no remainder. Same thing here. If x minus 2 is a factor, that means it's going to divide evenly with no remainder. Why do we care about that? Well, because remember, our goal is to be able to solve polynomials when factoring fails. So what we do is we use division to help us get some of these factors out. So if we look at example 8, it says solve the equation given that 3 is a 0 of f of x. Okay, now, if 3 is a 0, what does that mean? That means that it comes from the factor x minus 3. So if 3 is a 0, then x minus 3 is a factor. Think about if you set that equal to 0, 3 is the answer you would get, okay? So what that tells us, if I divide this polynomial by x minus 3, I should get a remainder of 0, which is good because it helps us determine how to write this function. So we want to divide out using a corner number of 3 for the factor x minus 3. So I get 2, negative 3, negative 11, positive 6. Bring down the 2. Multiply, add, multiply, add, multiply, add. Ding, ding, ding. That's exactly what we wanted. We should get a remainder of 0 because that's what the factor theorem tells us. Now, here's what I know, and this goes back to that division algorithm at the beginning. Remember we said if 5 goes into 25 5 times, then that means 25 is equal to 5 times 5. Well, if x minus 3 divides out to 2x squared plus 3x minus 2, then that means that this polynomial is equal to x minus 3 times 2x squared plus 3x minus 2. And that's equal to 0 because that's the equation we're solving. How do I know that? Because x minus 3 divided out of that equally. And once I divided it out, this polynomial is what we were left with. And now we can use, we've got a linear factor and a quadratic factor. We know how to solve both of those. So let's see if this is factorable. If it's not, then we got to use the quadratic formula or something else. But I think this one is factorable. We're going to get x minus 3 times 2x and x. I think we want a 2 here and a 1 here. We want a plus here and a minus here. So there's our factors. And so now we can solve this. We get x equals 3, x equals positive 1/2, and x equals negative 2. This was not factorable when we started. If you tried to use factoring by grouping, you're not going to get very far. But if they tell us what one of the zeros is, then we can use the division to get that factor out, which leaves us with something that is factorable. So again, pause the video and try number 9. Exactly the same thing. You're going to divide out the factor with the negative 1 in the corner, see what you get left, and see if what's factorable when you're done. Pause the video, come back in 3. All right, so check how you set this up with your division. Notice that if c is negative, when we subtract it, x minus negative 1, that means the factor we're looking at is x plus 1, okay? So x plus 1 times whatever we got left over when we divided, which was 15x squared minus x minus 2. Now, this is factorable, I do believe. Let's see what we get. Yep. Now remember, I don't care what method you use to factor as long as you can get it factored. If you need to go off to the margins and do scratch work and do factoring by grouping, do it. Whatever you have to do to get it factored, as long as you can factor it correctly, I am happy, whether it's guess and check or some other method. So here are our solutions. Negative 1, positive 2/5, negative 1/3. Again, that would not have been factorable at the beginning, and so this is what we can use, which is very nice. All right, that is the end for today. and we'll come back and start talking about zeros next.